Welcome to Section 4 of the Robert Shaw Uniline Division Fundamentals of Pneumatic Controls video training program. This section will provide a discussion on the operation and function of receiver controllers and their transmitters within a pneumatic control system. Section 3 discusses control theory and the operation of controllers and should be reviewed before proceeding with this section. The theories and applications discussed in this series are generic in nature and can be applied to any pneumatic control system regardless of its manufacturer. The receiver controller and its associated transmitter or transmitters provide a great deal of flexibility in the application of the controller within the mechanical system of a building. These devices provide the primary controls in most modern HVAC systems. Prior to the advent of the transmitter and receiver controller systems, remote bulb controllers, often referred to as master and submaster devices, were utilized. These controls had limitations as to where they could be located. The mounting location could be no further from the sensed medium they were controlling than the length of the capillary tube attached to the temperature sensing bulb or the pressure capsule in the case of pressure sensing. Shown here is an example of a remote bulb temperature controller or master controller. And this is an example of a submaster controller, the difference being the addition of a reset scale, which provides the ability to have an input from another controller, which will automatically reset the set point of the submaster controller over a specified range. This is dialed in directly on the controller itself. These master and submaster controllers had to be calibrated separately. As we get into the operation and calibration of receiver controllers, you will see the advantages of the transmitter and receiver controller systems. Here is an example of a Robert Shaw receiver controller. Its small size makes panel mounting easy and can provide the same functions as that of a master and submaster controller. Shown here is an example of our new modular style receiver controller. The main advantage of this controller is the modular design and size, which provides panel layout advantages. With a transmitter and receiver controller, the functions are split into controlling and sensing. The controlling is done by the receiver controller and sensing at the transmitter. A transmitter can be located anywhere, unlike the master or submaster. A transmitter can sense temperature, pressure, or humidity, and transmits a pneumatic signal of 3 to 15 pounds per square inch gauge, or PSIG, to the receiver controller, which may be mounted in a central or convenient location. At this central location, the signal being transmitted from the transmitter is piped to a receiver controller, or controllers, which then provide the controlling signals for the system. The centralization of the control functions allows the control devices such as logic relays and other necessary hardware to be conveniently located for calibration and service. This also allows control panels to be pre-assembled, tested, and calibrated in a panel shop so they are ready for on-site installation and hookup prior to the startup of the building. There are three basic types of transmitters used in HVAC control systems. They are temperature, humidity, and pressure transmitters. Let's take a look at the various types of temperature transmitters. The first of these is the room or wall transmitter. The room transmitter is designed for wall mounting and, like a pneumatic thermostat, has a decorative cover to conceal the sensing element. Rigid element transmitters are suitable for duct or well mounting. Rigid elements and rigid coiled elements are used for air duct sensing generally. However, the rigid element may also be used in an insertion well for sensing liquid temperature in piping. The bulb and capillary styles are used for sensing outdoor air temperature or where transmitter mounting is a problem and a remote sensing bulb is needed. Averaging elements are among the element styles used to measure temperatures in large ducts where stratification of the airflow may occur. There are two types of humidity transmitters: the room transmitter, which is wall-mounted like the room temperature transmitter, and the duct-mounted humidity transmitter, which is used to sense the relative humidity in an air duct. The humidity transmitter uses a very sensitive hygroscopic element to sense the relative humidity in the air. One must be very careful not to touch this element, as the oils and acids from the skin will deteriorate the accuracy of the device and render it useless. The pressure transmitters fall into 4 distinct styles. These are single input pressure transmitters, dual input or differential pressure transmitters, and differential static pressure transmitters. Shown here is our 2301 series pressure transmitter, providing sensing ranges from -10 to +300 psig within the various available models. The differential pressure transmitter is available to read differential pressure varying from 0 to 50 and 0 to 100 psig. Differential static pressure transmitters are available in several ranges from -0.5 inches of water column to +10 inches and are used in the control of building static pressures, duct static pressures, and other low-pressure applications. Now, let's take a look at how the transmitter operates. These principles are true for all of the transmitters in our product line and most competitive devices available in the HVAC industry. The operation of the transmitter is dependent upon a constant source of main air supply. This source should be maintained at 20 psig. The main air supply is fed to the transmitter through a restrictor, which feeds the branch pressure line from the transmitter to the receiver controller as shown on this piping diagram. The Robert Shaw transmitter is sized to receive its air supply by means of a 7/1000 restrictor being fed a 20 psig main air supply. This will provide a flow of 1 SCFH, or standard cubic foot per hour, of air through the restrictor. This flow or volume of air is provided to the branch line as the source for the branch line signal, which is then regulated by the operation of the transmitter. Shown here is a close-up of a transmitter. It is a one-pipe device and operates like a one-pipe pneumatic room thermostat. The difference being that it has a fixed span or range. Transmitters are direct acting devices. As the sensed medium increases, the branch line signal pressure increases. Shown here is a simplified cutaway of a transmitter to show the operation of this device. The transmitter provides the ability to bleed air to atmosphere as the sensing element opens and closes the leak port, thus allowing the transmitter to maintain an output or branch line signal in relation to the sense condition. As previously mentioned, the transmitter has a fixed range. For different applications or temperature requirements, the different transmitter ranges must be selected for each application. In contrast to a thermostat, the transmitter has no set point. Its output is over the full range or span of the device. For example, a 0 to 100 degree transmitter has a span of 100 degrees or 100 engineering units, each unit being 1 degree. The output or signal pressure that is maintained by the transmitter is 3 to 15 psig over the specific range of the transmitter. This is an output span of 12 psig and relates to the temperature, pressure, or humidity being sensed. The degrees, percentages, or pounds, etc. are referred to as engineering units. Sensitivity is a term that is used to relate this ratio of engineering units to the output pressure span and is arrived at by dividing the output span of the transmitter, 12 psig, by the specific range of the transmitter. This provides the pounds change in output per engineering unit change. This is a sensitivity chart for the various Robert Shaw transmitters. Examples here are a 0 to 100 degree transmitter having a sensitivity of 0.12 pound change per degree of temperature change. A +40 to 240 degree Fahrenheit transmitter will provide a 0.06 pound change per degree of temperature change. With a pressure gauge and knowledge of the sensitivity of the transmitter involved, the sense temperature can be obtained. To make this easier, receiver gauges are used. A receiver gauge has a 3 to 15 psig range to match the output range of the transmitter. Shown here are the 3 common sizes of receiver gauges. Gauges are available for mounting directly to a panel face or for mounting directly to the face of a receiver controller. Robert Shaw includes with its receiver gauges an overlay kit. This kit provides the most common transmitter ranges on peel and stick overlays that may be applied to the face of the receiver gauge to allow reading engineering units directly from the gauge face. This eliminates the need to calculate these readings or to obtain a specific gauge with the appropriate scale range on it. There are two types of receiver controllers. The single input device, which utilizes the input from a single transmitter and provides the similar function to a master controller or a remote bulb type controller. The second type is a dual input device, which utilizes the inputs from two transmitters and provides a reset function similar to that of a master and submaster control system. The receiver controller can provide either a direct or a reverse acting output in relation to the sensed variable. It should be noted that the transmitter is always a direct acting device, and the receiver controller itself provides the proper action. Receiver controllers also provide the option of selecting models with remote set point adjustment or control point adjustment, sometimes called CPA. This provides the ability to remotely adjust the set point of the receiver controller by varying a 3 to 15 PSIG input signal with a device such as a gradual switch or pressure regulator. This adjustment is generally limited to a percentage of the primary input transmitter span and may amount to an adjustment of 20 to 30% of the primary transmitter range, depending upon the receiver controller used. For example, using a 0 to 100 degree transmitter, a plus and minus 10% CPA could change the set point 10 degrees up and 10 degrees down for a total of 20 degrees CPA control, or 20% of the primary transmitter. An example for this type of application might be a panel containing receiver controllers with gauge readouts piped to a central control location or operating console. In response to a change in the system requirements, a remote adjustment could be made from a central control panel, raising or lowering the set point of the receiver controller by varying the 3 to 15 PSIG input to the CPA port on the receiver controller. Take this opportunity to stop the tape and answer the questions in your study guide. You may want to review all or part of this tape before continuing on with the rest of this section. Each receiver controller has the ability to provide an adjustable throttling range. Note here on the receiver controller the adjustment slide representing the throttling range adjustment. The scale is calibrated as a percentage. The throttling range percentage represents a percentage of the primary transmitter span, which is sensing the controlled medium. To determine the percentage of throttling range to be dialed in on the receiver controller, the desired number of degrees or engineering units throttling range is divided by the total span of the primary transmitter in engineering units and multiplied by 100 to get percentage. For example, if we're using the 0 to 100 degree primary transmitter and a 15 degree throttling range, the formula is 15 divided by 100, which equals 0.15 times 100 and yields a 15% throttling range. The throttling range is determined by the application being controlled. For instance, space temperature versus the discharge temperature of a hot deck or cold deck, or the temperature of chilled water. The old adage of tight enough for good control, yet wide enough to prevent hunting, still applies. Some examples of typical throttling ranges are: space temperature would normally be in the range of from 3 to 6 degrees. Coil discharge temperatures could be somewhere in the range of 10 to 15 degrees. Cold or hot water may need to be 20 to 30 degrees, depending on the system and valve sizing. Receiver controllers of different manufacturers utilize different port designations. This is a 2341-001 model made by Robert Shaw. Port designations on this device are: 1 for the primary input, 2 for the remote set point adjustment, 3 for the secondary or reset input, M for main error, and B for the branch line output. Contrast that with our 2341-500 series, which is a new modular device. It utilizes an S designation for the primary signal input, R for the reset or secondary signal input, C for the control point adjustment or remote set point adjustment, M for the main air supply, and B for branch line output. This is a chart showing the port designation of some competitive devices found in the field. A complete chart is included in your study guide and in the instruction booklet that is provided with our 900-012 receiver controller calibration kit, which we will discuss and use later in this presentation. You are looking at a typical application of a single input receiver controller found in the field. This is a coil discharge control application with the primary transmitter sensing discharge air temperature. The transmitter provides a signal to the S port of the receiver controller. The branch port of this receiver controller is piped to a normally open control valve. The branch line output pressure to that valve changes in response to changes in the discharge air temperature. Now, let's take a look at this same application with the addition of a remote set point adjustment. The difference is the addition of another input on the C port or control point adjustment port of the receiver controller, allowing us to remotely change the calibrated set point of the receiver controller. Let's go through the calibration procedure utilizing our 900-012 receiver controller calibration kit. We will utilize this kit because it provides a handy frame of reference for producing inputs to the receiver controller. We refer to this type of calibration as bench calibration because of the ability to adjust the inputs to any value desired. The most predominant feature of the receiver controller calibration kit is the multi-scale gauges that allow you to read temperatures directly from the gauge scales. The next feature is the pressure regulators used to adjust the output pressures indicated on the gauges. A main air input is applied here, and the simulated transmitter outputs to the receiver controller are attached here at the P port for the primary sensor and here at the S port for the secondary sensor. We will be using only the primary signal for the single input calibration. We need to connect main air to our calibration gauges and to the receiver controller, and connect the primary output of gauges to the primary signal port of the receiver controller. The calibration steps for a single input receiver controller are as follows. For this example, we will use the 0 to 100 degree scale to simulate a 0 to 100 degree transmitter. Set the throttling range to the desired point. We will use a 10 degree throttling range for this example. 10 divided by 100 is 0.10 or 10%. So, move the throttling range slide to the 10% mark. Set the authority slide to 10% or the minimum setting. Set the input pressure or reference temperature on the primary input receiver gauge to a value within the range of the transmitter to be used. Adjust the control point adjustment to match the temperature reading by adjusting the branch output pressure to 9 psig, or the midpoint of the spring range with the calibration tool. Adjust the control point scale to match the calibration point by lifting the ring and turning it to match the input from the primary transmitter. Note the control point scale is marked 3 to 15 psig. This corresponds to the 3 to 15 psig output of the primary transmitter. Adjust the control point adjustment with a calibration tool until the control point scale indicates the desired set point. This is done by calculating the transmitter output pressure at the desired temperature. To make this easier, overlays for the control point scales are available in ranges to match the ranges of most popular transmitters. They are applied by peeling the scale from its backing and applying it to the control point scale ring. Once the calibration is made and the control point scale is set, all adjustments must be made with the set point adjustment using a calibration tool. If the control point scale is lifted and turned, the calibration reference is lost. This receiver controller is calibrated and can now be installed in the system and set to the desired set point. To calibrate a receiver controller in the field, it must be calibrated to the transmitter input. Set the throttling range slide to the desired point. Set the authority slide to 10% or the minimum setting. Note the input pressure or reference temperature on the primary input receiver gauge. Adjust the control point adjustment with the calibration tool to match the temperature reading by adjusting the branch output pressure to 9 psig or the midpoint of the spring range. Adjust the control point scale to match the calibration point by lifting the ring and turning it to match the input from the primary transmitter. Adjust the control point adjustment with a calibration tool until the control point scale indicates the desired set point. The calibration procedure when utilizing a control point adjustment input is similar with one exception. You must set the input on the CPA port first. The control point adjustment on the 2341-500 series can change the set point 20% of the primary transmitter range. This means with a 0 to 100 degree transmitter, the CPA can change the set point 20 degrees. To have the ability to increase and decrease the set point 10% of the primary input with the CPA, we must calibrate the receiver controller with 9 psig on the CPA port. Adjust the CPA port input to 9 psig. Set the throttling range slide to the desired point. Set the authority slide to 10% or the minimum setting. Note the input pressure or reference temperature on the primary input receiver gauge. Adjust the control point adjustment to match the temperature reading by adjusting the branch output pressure to 9 psig or the midpoint of the spring range. Adjust the control point scale to match the calibration point by lifting the ring and turning it to match the input from the primary transmitter. Adjust the control point scale to indicate the desired set point by turning the control point adjustment with the calibration tool. An increase in pressure on the CPA port will increase the set point, and a decrease will decrease the set point. This example illustrates the dual input receiver controller piping. The primary transmitter is inserted into the hot water supply piping downstream of the mixing valve. The secondary transmitter is measuring the outside air temperature, and the receiver controller is controlling the mixing valve. To set up and calibrate a dual input receiver controller, it is necessary to understand the reset schedule. A reset schedule is the changing of the set point on a controller based on the change of a second input. When the outside air temperature drops, it is necessary to increase the temperature of the water heating a building in order to keep up with the increase in heating load. This example of a reset schedule shows the changes in set point for the receiver controller based on a relationship to the changing outside air temperature. At 55 degrees outside, the hot water supply need only be 110 degrees. However, as the temperature outside begins to drop, it is necessary to increase the temperature of the hot water. When the temperature outside drops to 5 degrees, the hot water supply must be reset to 190 degrees. Authority is the effect of the reset signal from a secondary transmitter on the set point of the receiver controller. It is expressed as a percentage of the primary signal from the primary transmitter. This is the formula for calculating authority. It reads, the delta T of the primary reset times the primary transmitter sensitivity plus the throttling range in degrees times the primary transmitter sensitivity divided by the delta T of the secondary reset times the secondary transmitter sensitivity and multiplied by 100 to get a percent. The delta T of the reset is the difference between the upper and lower range of reset schedule. For this example, the primary delta T is 80 degrees and the secondary delta T is 50 degrees. The sensitivity of the 40 to 240 degree primary transmitter is 0.06 psig per degree of change, and the minus 25 to 125 degree secondary transmitter sensitivity is 0.08 psig. Sensitivity was covered earlier in this program and should be reviewed if necessary. For this example, a 20-degree throttling range is being used. The formula now looks like this. 80 times 0.06 equals 4.8. 20 times 0.06 equals 1.2. 50 times 0.08 equals 4. 4.8 plus 1.2 equals 6. 6 divided by 4 equals 1.5. 1.5 times 100 equals 150%. Bench calibration of a dual input receiver controller utilizes the receiver controller calibration kit described earlier in this section. First, set the throttling range for 20 degrees. 20 degrees is 10% of the 200 degrees primary transmitter range. So move the throttling range slide to the 10% mark. Next, set the authority slide to the 150% mark as calculated in the example. Set the primary and secondary inputs to the midpoint of the reset schedule. The primary is set to 150 degrees, reading on the plus 40 to 240 degree scale, and the secondary to 30 degrees on the minus 25 to 125 degree scale. Adjust the control point adjustment to get a 9 psig branch line output. Lift and rotate the control point scale to 150 degrees, or 9.6 psig. This represents the input from the primary transmitter. You can simulate a change in outside air to check the authority setting. Change the secondary input to represent 5 degrees. The branch line pressure will drop, which will open the normally open heating valve to increase the temperature in the pipe. Now, increase the pressure on the primary input slowly until the branch pressure is back to 9 psig. The primary input gauge should read approximately 190 degrees. Now, adjust the secondary input to the other end of the reset schedule, 55 degrees, and readjust the primary to get 9 psig on the branch line output. The primary gauge should read approximately 110 degrees. This concludes the bench calibration of the dual input receiver controller. It may be connected into a system with transmitters as long as they are of the same ranges as those used in the calibration procedure. To calibrate a receiver controller in the field, we must first plot the reset schedule on paper before starting. In doing this, we will know what the set point should be at any given outside air temperature. With a piece of graph paper, mark the ranges of the transmitters, primary on one axis and the secondary on the other. Find the points where the primary and secondary values intersect at one end of the reset schedule. For example, our reset schedule tells us that at 5 degrees outside temperature, our hot water set point is 190 degrees. Find the point where primary scale 190 degrees intersects with secondary scale 5 degrees and put a dot. Now, find the point where the other end of the reset schedule intersects. Primary 110 degrees and secondary 55 degrees. Place a dot there. Draw a line from one dot to the other. This line can continue through and beyond on both ends. The appropriate set point can be determined on this chart, regardless of the outside air temperature. Calibration of the dual input receiver controller in the field is accomplished by first setting the throttling range and authority, as described earlier. Remember, if any changes are made to the throttling range or authority settings on a receiver controller, it must be recalibrated. Take note of the input signal on the secondary transmitter input. For this example, let's say it is 20 degrees outside. Turn the control point adjustment until the branch line pressure equals 9 psig, or midpoint of the spring range. This calibrates the system to the current primary input. Lift and rotate the control point scale to indicate the current control point at the primary transmitter, In this case, the primary transmitter is reading 150 degrees or 9.6 psig. Find where the current outside air temperature intersects the reset line. Move down to read the proper set point of the controller, which is 165 degrees. Turn the control point adjustment with the calibration tool until the set point scale indicates the proper set point. In this case, 165 degrees Fahrenheit or 10.5 psig. This concludes the video material for Section 4, Receiver Controllers. Take this opportunity to stop the tape and answer the questions on this section in your study guide. You may want to review some or all of the material in the Receiver Controller section before proceeding on with the next section. For more information about the devices discussed here or other tapes covering Robert Shaw control devices, contact your local Robert Shaw Uniline wholesaler or write to us here at Robert Shaw Controls Company, Uniline.